Welcome to the Introduction to Energy. So energy is the ability to do work or produce heat. Now work is defined as motion against an opposing force. Now note that motion without an opposing force is not work. So in order to do work, you have to have motion and you have to have a force that's being opposed. So the Earth orbits the Sun, but it doesn't do any work in orbiting the Sun because there is a force being applied to the Earth, but that force is being applied towards the Sun, which is not against or towards the direction of motion. It's perpendicular, right? Because if the Sun is here and the Earth is there, well, that force is being applied, the force due to gravity is pulling down towards the Sun. But the Earth isn't moving that way. The Earth is moving around the Sun. And so as the Earth moves this way, that force is always perpendicular to it, which means there's no force being opposed. So the Earth is moving, but it's not doing any work. There's no work being done on it because that motion is not opposing a force. Likewise, if I were to, say, lean against a wall, I may be pushing against that wall. The wall is pushing back on me, because of course any action has an equal and opposite reaction. So I'm pushing on the wall is pushing on me, so I'm opposing the force that the wall is exerting on me. But if the wall doesn't move, then I haven't done any work. I may have expended energy, but I haven't done any work. And this is the difference between energy and work. Work requires motion, and it requires that that motion be against an opposing force. So, if I, say, take a ball and I lift it against the force of gravity, now I'm doing work. But if I throw the ball perpendicular to the force of gravity, I'm not doing any work. Because, yes, I'm accelerating the ball, but I'm not opposing any force. Inertia is not a force, right? I'm accelerating the ball. I'm putting energy into the ball, but I'm not doing any work on the ball. So, we also have the law of conservation of energy. Energy cannot be created or destroyed. It can be converted from one form to another, but no energy is gained or lost in the process. So, when I exert energy to lift the ball against the force of gravity, my body loses energy through chemical reactions, and in doing so, I'm lifting the ball. I'm creating some heat. I'm losing some of the energy towards heat, heating up my body and the air around me and maybe the ball a little bit, but I'm also lifting the ball. The ball has gained energy because it's now farther from the Earth's surface. And so we have two different main types of energy. There's kinetic energy, which is the energy an object has due to its motion, and potential energy, which is the energy stored due to an object's position. Now, kinetic energy, the motion, one example of this may be a bowling ball rolling towards the pins, and the energy that it has because it's moving, that's the kinetic energy. Now, an example of potential energy may be a roller coaster that's at the top of a hill. That has potential energy because it's been raised up above Earth's surface. Now, as that roller coaster goes down the hill, it loses some potential energy. It's converting some of the potential energy into kinetic energy. It speeds up as it goes down the hill. And then once it reaches the bottom, it's reached the minimum of its potential energy, but the maximum of its kinetic energy. And then, of course, it may climb up a subsequent hill. And in that way, it's then converting some of that kinetic energy back into potential energy. Now, the unit of energy, or the unit that we use to measure energy in the SI, is the joule, named after James Joule. And so, 1 joule is defined as 1 kilogram times meter squared divided by second squared. Now, that seems like a little bit strange of a unit to be using because it doesn't seem to, what is a kilogram meter squared per second squared? Well, remember that work is motion against an opposing force. Now, force is measured in newtons, and 1 newton is 1 kilogram times meter divided by second squared. And since motion is measured in meters, that means that when we multiply the force times the motion in meters, we have a newton times a meter. Now I'm plugging in 1 here because the number in front doesn't matter. So we have a newton, which is a kilogram meter per second squared, and we're multiplying by meter, so now we get a kilogram meter squared per second squared, and that was 1 joule. Right? So the unit of energy, the joule, is defined using work. That's how we're defining our unit here. So work has the same units as energy does, and we have a few different types of, a few different units that we may measure energy in. In science, we generally use joules. We may use calories or capital calories. This calorie is really 1,000 calories. So this is the calorie that's listed on food products. So if you open up a Snickers bar, let's say, and it says it's 200 calories, that's really 200 of these capital C calories. It's really 200,000 lower C calories. That's a lot of energy. We also may use an electron volt, which is the amount of energy an electron has if it's accelerated by through a potential field of 1 volt. We may use British thermal units or BTUs in things like air conditioners or central heating. We use therms to measure things like natural gas, how much energy is contained in some volume of natural gas. We also use tons of TNT. TNT is trinitrotoluene. This we generally use for very, very large amounts of energy, like nuclear explosions. So that was an introduction to energy.